That's good. This is either going to be really short or really long. I'm not sure which. Yeah. Okay, so this is not going to. Okay, so I'm taking a break from like detailed level discussions. Like this is going to be like super high level. You know, it's going to start with a bunch of pictures. But this is sort of my plug for parallel Matlab. Okay, so I sort of originally designed this because like we keep telling, our group especially, keep telling a lot of other people that we just use Matlab, you know, but we talk about a lot of things that we do distributed, which confuses a lot of people. So this is just gonna show like how that's possible and how we do that. Okay, so first I'm gonna start with like the motivation, right? So the motivation essentially is, if I can get this, yeah. It's a conservation of complexity in terms of what a student needs to do in terms of focus, attention, and time. Because these are, from the beginning of time to now, like graduate students spent about, you know, like 4 to 6 years in grad school, and that's really about it, right? That's not gonna change, right? But the things a grad student have to learn and to deal with have exploded dramatically, right, in the past, you know, century or so. So a grad student in the 1900s and a grad student now sort of has to learn, sort of has to know about a lot more things. A grad student now. So, and that's very quickly untenable, right? Because if you think of what a student has to do in exploration geophysics, there's a lot of areas of knowledge that we have to know about, right? So there's math, physics, signal processing, and then to actually get a code to run, you have to learn about programming, computer architecture, and then now increasingly optimization becomes more and more important. In this sort of hexagonal diagram, you sort of have a student that's trying to wrestle with all of these, right? And it can specialize in some of these things. So you take like a theoretically inclined student, maybe has a heavy math background, knows a lot about math, knows a lot about physics, a bit about signal processing, but not so much about computer architecture and programming. Okay, tends to write high-level script programs. Okay, that's sort of, you can sort of see like the tension was spent in that green area. You take someone who's more computationally inclined, maybe graduated from engineering or computer science, knows a lot about programming, optimization, computer architecture, maybe needs to study up a bit on latest applied math and physics, signal processing, you know, but sort of come at it from the other end. But that's sort of what they spend the majority of the time on. So you get sort of these two divides, these two different archetypes of students. And their commonality is that that shaded area in the middle is sort of constant, right? Because that shaded area in the middle sort of represents just the time spent in a program. So you can focus on several of these things, but it's very rare for a student to just grow in all areas. There's very special cases of very, very good people who just gets good at all of these, but that's very rare. Usually you have to sort of, it's a zero-sum game, right? Because your time is a very limited resource. So I'm not gonna trust this anymore. Just gonna use keyboard. So you also sort of, so basically what happens with a lot of seismic processing programs that we run and also imaging and basically many scientific code that ends up being a trilemma of things that, you know, of qualities that it has. So you sort of have, you know, like you want your code to be sophisticated, you want it to run fast, but you also want it to be easy to implement, right? Like these schemes that we come up with. So it's almost always a choose-two kind of situation. So you either have a code that's very sophisticated and runs very fast, but that becomes very hard to maintain, right? Or you have something that's sophisticated and easy to implement, but it usually ends up being in a pure scripting language then, right? Or like a pure Matlab thing. Or you want something that runs fast and is easy to implement, but that's usually already done. So those are all usually like low-hanging fruits that, that people in the past few decades have sort of implemented. So to sort of get out of this kind of trilemma, you sort of need some level of abstraction. So what do I mean? Well, what happens with code that, well, okay, so you may look at this diagram and say, okay, so maybe if you always have to choose two, maybe I just pair like someone who's really strong in theoretics and someone who's very strong in writing computational code and just sort of pair them together, right? You have a theoretically inclined student, computationally inclined student. They work together, you know, and they write something that's beautiful. Well, usually what happens, though, is that you take some high-level script that a theoretical student wrote, and then you say, you guys work together. So what usually happens is a low-level fork gets created right? From a scripting language sample code. So one student says, oh, okay, I'm really good at optimizing this, right? So I'm just going to take what you've done, I'm just going to go implement this in very low-level Fortran or even assembly and just like hand-tune everything. Meanwhile, the other student goes, oh, there's other ideas I want to try. So they tries to go and plays around with the high-level abstraction a little bit. And eventually what happens is these two things will diverge, right? So you have, you have basically just different things going on with the code. And one of two things happen, right? So, the low-level code usually becomes a feature stagnation thing where it gets faster and faster, more hand-tuned, and a lot of people uses it, but it sort of doesn't do anything new other than being really, really fast and does things really well. Yeah. So, and the scripting, the program just basically sort of ignores everything that the low-level code is sort of doing, because by then the original script code probably have morphed, or that guy probably will have graduated and sort of unrecognizable anymore. So that's usually what happens. What is desirable, obviously, is somehow these two can work together, right? That's sort of the dream. So somehow a theoretically inclined person and a computationally inclined person come together and work on a unified code base. Okay. So that's sort of the ideal situation. It usually doesn't happen, but that's sort of the dream. So I'm just going to talk about what it takes to achieve that kind of thing. Well, first of all, which language or package? So the very first insight we had is basically why use the same language or packages, right? Why does one, like a lot of programs are actually built on many, many pieces that use many different languages and packages, and they're separated on many different levels. So, because designing algorithms and designing computational kernels or engines have very different needs, right? For an algorithm design, you want something that's flexible, you want something that's easier to understand, easy to debug, sort of as close to the mathematical expression as possible, right? And something that encourages experiment. Whereas computational kernels or engines, you want some very well-defined behavior, and you want languages that have mature compilers that can optimize a lot of these things. You want low-level access to a lot of system routines, allows tweaking, and hopefully works well with parallel systems. So these two typically are different parts of the code. Okay, so usually they don't have to be within sort of the same file. They're usually not in the same file. They're not in the same routines. They're sort of separated out a lot in many, many code bases. And what tends to happen is you get this call signaling kind of relationship between the algorithm code and the computational kernel code, right? So this happens everywhere. So for example, basic shell scripts. So on one hand, you have like seismic utilities, right? Like your SCP code, like RSF Madagascar. Basically seismic or seismic Unix, like a lot of these tools that people have used that are written in sort of low-level languages. And to drive them, your algorithm basically is just a shell script, right? That's basically what happens a lot in academia. It's fancier if you're in like a contractor and position, and you sort of basically have similar things. You're just sort of more fancier, right? Like you build workflows, and then the workflows go and calls sophisticated computational code. Even if you write a lot of your code in low-level languages, like C, C++, Fortran 90, you don't usually write yourself a lot of the very, very low-level fundamental code. A lot of times you would depend on like BLAST libraries or FFTWs or map kernel libraries, right? The Intel package to basically do the very, very, very low-level things. Okay. Like you wouldn't write a matrix routine yourself, even though you write the rest of the programs in C. Okay. So basically the same kind of situation actually happens within Matlab itself. So Matlab, a long, long time ago, was originally written to interface with LAPACK routines. Okay, that's what it was for. It's like a matrix laboratory, right? It's designed to easily spin up some matrices, and then you sort of throw them at LAPACK very easily. Like it's designed so that you don't have to call LAPACK routines yourself. And you can realize then, looking at this, that MATLAB itself sort of embodies this kind of philosophy. You just sort of have to use it the right way. You don't want to write the low-level stuff in the MATLAB scripting thing, like writing for loops inside MATLAB. The fastest way is, of course, like vectorization, right? That's what this means. Like vectorization means means MATLAB recognizes that you have a large chunk of data, you want to sort of matrix multiply or do some reduction operation, like it calls then laypack routines or scalar pack parallel MATLAB, or some other MEX files that you ran, that you wrote and compiled. So basically what is needed in order to sort of avoid this code divergence and to sort of improve productivity is, of course, abstraction, right? So that's sort of fundamentally what I'm getting at. Abstraction, the abstraction layer is very, very important to not get stuck in a situation where you hardcore optimize some code and it becomes unmaintainable, and then people sort of lose scientific interest in that thing. So this thing is very, very hard to balance, and it's obviously an open problem of how to design abstraction layers across all different parts of computation. But it's something that we had at SLIM are taken advantage of to do parallel computations. Okay, and that abstraction layer is parallel MATLAB. So what is parallel MATLAB? Well, officially, parallel MATLAB is just another toolbox, right? It's like the signal processing toolbox, it's like the image processing toolbox, it's like the statistical toolbox or the optimization toolbox. Like that's what it sort of officially is. So it's just another piece of code that you can license. You know, it's another like just you know however much toolboxes cost for MATLAB, and it comes with it a bunch of code that basically is written to do parallel execution. So that toolbox itself has basically all the code base, and it can spawn local workers. I'll say what workers are later. But that's different from what MATLAB calls a distributed computing server, which is a separate product, right? Which basically builds on the toolbox, and the only difference is that it allows you to spawn workers on external nodes in a cluster, basically just not locally on your own computer. Okay, so that's usually what people want in parallel processing. But some people basically just want, you know, like if your code is inherently very parallelizable, like a toolbox, just toolbox version, like be able to spawn many workers on your own computer is enough to speed up your code. Some people sort of need that, but for our purposes, we talk about parallel MATLAB, we usually mean workers basically spawn on external computers. That's not your own local computer. And it's not, so MATLAB itself has a scheduler, but you don't have to use theirs, right? Like, so at SLIM we just basically hack torque into it. Well, it's not hacked, it's officially supported. that word may be very questionable sometimes, we feel. And on Umoha, basically it's built on Slurm, right? Okay. So why did we choose to use parallel MATLAB? Well, previous to 2009, right? So SLIM actually mostly used SciPy, NumPy kind of workflow. And this is like way before NumPy was 1.0. This is when Travis Oliphant was still selling manuals to NumPy to fund his development of NumPy. And so that's sort of like, we use that to write our kernel, and then our interface is like most seismic utilities, right? So at this time, we chose ours to be the same as RSF or Madagascar. We even had like a symbolic math, like domain-specific language, which is called SymPy, which translates math expressions and then basically translates them into shell scripts that calls, you know, seismic routines. So what we wanted to do was to look for something that can has native support for parallel arrays. Because at the time, we were doing a lot of multilinear transforms, and we work on very, very large data, and we just needed something that basically recognizes a distributed array as a distributed array. Basically something that looks like a shared memory computer, okay? So there are two candidates. For Python, there was something called StarP, and MATLAB itself just added support for distributed arrays. So in the end, we sort of went with MATLAB on a hunch. Actually, it was just cheaper, because StarP was really expensive. And it turned out to be the right choice, because StarP eventually got acquired by Microsoft and just sort of died in 2009. So we sort of dodged a bullet there. So what is it allowed to do? Well, MATLAB basically always assume a master supervisor for a pool of workers, and each worker are just independent, separate MATLAB processes. They're full MATLAB processes, okay? They're just recognized as workers, and they can live, they basically live either on your local machine or on remote machines. And these workers all sort of form a pool. And they could be provisioned, and you can release them from just interactively from the command line. Again, local workers are free with the toolbox, and the pricing is individually licensed for remote workers. So the main interest we had with distributed MATLAB is support for distributed arrays. And it emulates, what essentially it is, it emulates a normal numeric array. So by default, it's when you construct a distributed array, it sort of distributes over the last dimension equally across all workers. And you can, there's APIs to change sort of, how the array is distributed. And it can be, there's a lot of constructors for these things. You can construct them locally from the workers themselves or from the master. So it basically maps to like the shared memory or the NUMA kind of like archetype, right? So this is like an easy way to get your feet wet for a graduate student to do these kind of things. Now, it has one very important killer feature, which is a lot, and I mean a lot, of MATLAB functions work directly on distributed arrays without modification. Okay? And they all have the same name. It's not a different namespace. So what do I mean? Well, here. All these functions, okay, like your log, your length, and importantly, like all your matrix divides, all your powers, dot times, dot transpose, norms, basically a lot of these things that you recognize that work on local numeric arrays are completely overloaded for distributed arrays. Like you name your array something, right? X. You call like cosine X. Doesn't matter if it's a local array or a distributed array. It just happens. Like it just does it. Okay. And this is just page one. Like there's page two. So there's a lot, and there's more. Like every single release, they keep adding more and more stuff into it, right? There's even like Ig, stuff like that. Some of these are just like some people's PhD thesis. So that's sort of what distributed arrays sort of buys you in terms of MATLAB, right? So, and the powerful thing is it allows many of our code base to work directly. Our existing code base that we write for serial programs to work just directly on distributed arrays with very few changes, and allows us to collaborate with people that's in pure applied mathematics who only write scripts that work on their own machine. And it basically just allows us to trade, basically licensing fee for students' time. Okay, so and that turned out to be a very, very good trade-off, especially considering how student times is always sort of constant. So it's sort of not that slow. Okay, so this is a high-performance LIMPAC. This is a distributed matrix inverse in 3 lines. Okay, a distributed constructor for the matrix, distributed constructor for the vector, and then you just do A/B. That's it. And so I just did this afternoon, right, on a small benchmark on Emoha, 128 nodes, 8 processes, 1,024 processes total, inverting a 1.8 million by 1.8 million matrix, which is about 360 gigabytes, or 80, took basically 10 minutes. So that's about 12 teraflops, which is fairly respectable considering this is 3 lines, right? Yeah. Okay. And verification code. This looks like code that runs normally on a serial computer. Okay, but this is to verify basically the errors of that. As long as it's not over single precision, relative machine tolerance, it passes. But look, like you could recognize a lot of these things. These are not special distributed namespaces. These are just basically functions that you recognize that work directly on these distributed arrays. We basically built Spot and P-Spot. I think because of time, I'm not going to talk about it, but it basically is a way for us to abstract the notion of multilinear things. So you do, for example, Fourier transform, you do Fourier transform on one dimension, you transpose and then do Fourier on another one. The gist is I implemented SRME multiple prediction on this thing, okay? And again, I just ran a small benchmark this afternoon. The same instance, seismic line is like 2,000 times samples, 2,000 shots, 2,000 receivers per shot. It's about 42 gigabytes of data in single position. Took about 12 minutes for the SRME prediction step using FFTs. Okay. There's other things too. I'm almost finished. There's just other things too aside from distributed arrays, although that is pretty killer. So there's support to do parallel loops, simple parallel loops that you just have a parallel index and it tries to split that parallel index across your number of workers. It has support for a associative reduction operation, so it recognizes that and allows you to use the parallel index within those kind of functions. So it's a simple way for students to learn about sort of map-reduce paradigm, okay? And at the latest release, Matlab also has support for real MapReduce. You can connect to Hadoop and stuff. And finally, it has something called SPMD, single program multiple data, which is what most people will be familiar with. Each worker has a local execution space, and then each worker runs sort of the same program. And so this is very easy because it's just a pragma, and then so it's very easy for a student to just include this in their program and learn about like the unified parallel C or bulk synchronous programming kind of style, because that's what this is, right, with barriers and stuff. And it's got MPI primitives, so you can go and learn about this. This is what an SPMD block looks like. You just initiate SPMD, each worker has his own thing, and then you end the SPMD, so this is outside now. And each worker, basically this local variable just turns into a composite object, right? Curly braces, and you can index into it. Things. Has detailed communications, you can do lab send, global concatenation, barriers, probing, send, receive between different workers. So it basically has a lot of these MPI primitives that you recognize. Okay, so that's pretty much it. So that's my plug for Matlab. Student time remains basically constant, right? So we need more and more powerful abstractions. And I believe Matlab is sort of doing sort of a good job on the abstraction side at least. There's a lot of complaints on other aspects, okay? Parallel Matlab. But I think at least on the abstraction part, it has sort of allowed us to do a lot of scientific work for very, very, very few effort needed to sort of babysit parallel programs. I mean, we still do. They're parallel programs. They always break or it's very slow. But at least we don't have to dig into very, very low-level stuff to get them to work in the first place. Okay. So that's it. I think Felix can attest that like since we've used Parallel Matlab, basically our cluster became unbearably busy, from basically sadly empty, sort of almost over a period of just a few months. So that's I think it's a great thing for scientific productivity, and it's something that if you haven't really invested in a parallel paradigm, it's something that can easily get your feet wet in parallel style programming. And that's it.